So let's get started on some of the homework in section 9.1. And again, we're going to be applying these square root concepts to radicans that are a little bit more complex than just simple whole numbers or counting numbers. So in our first two examples, I kind of want to look at and to show you the difference between these two. So the first, we have the square root of 25 plus 144. And in the second one, we have the square root of 25 plus the square root of 144. So what's the difference between these two? Well, going back to our order of operations, we want to go ahead and simplify. Just remember the absolute value symbols. Even though the absolute value symbol is not a set of parentheses, we treat it as if it is, and we go ahead and simplify what's in it first. The same thing can be said of the radical signs or our root symbols. So we want to make sure that we go ahead and simplify what's in it if possible. So that's not always going to be possible, but in this case it is. So 25 plus 144 would be equal to the square root of 169, correct? So 25 plus 144 is 169. Whereas this right here has it separated, so you can't really simplify anything underneath this. You need to go ahead and just solve it. So take the square root of 25, take the square root of 144, and then add them together. So in this case, we would have 5 plus 12, correct? So the square root of 25 is 5, and the square root of 144 is 12. So that means that 5 plus 5, 5 times 5 equals 25, and 12 times 12 equals 144. So 5 plus 12 equals 17. So if you take the square root of 25 and add it to the square root of 144, your answer would be 17. But what about this one? The square root of 169 is 13. So we're getting two different answers because they're written in a little bit different way. So we just kind of want to see the difference between those two problems. So let's come over to having a variable underneath. So what's the square root of b squared? So there's two ways we can look at this. We can look at it in the same concept that we're dealing with just our regular constants that are underneath the radical sign. So what times what equals b squared? Well, b times b equals b squared, correct? So we know that this is going to equal b, because b times b will equal b squared. Another way to look at it is this square root cancels out that, they cancel each other out. So the square root symbol and the exponent of 2 actually would just cancel each other out, and you just be left with a b by itself, or equals b. So just keep that in mind. If you have a square underneath a square root, those two things cancel each other out. Taking the square root of a perfect square will just leave that base. And we'll come down to this one next, the square root of 100y squared. So now we've got two pieces. We have a coefficient and then we have a variable with an exponent. So what's the square root of 100? What times what will equal 100? What times itself? So we know that's going to be 10. 10 times 10 will equal 100. Therefore, the square root of 100 would equal 10. Now, what's the square root of y squared? Again, that y squared and that radical sign are going to cancel out, and you'll just be left with a y. So there's another way to look at this too that we're going to see in this next problem that we're going to do together. But the square root of 100y squared is just 10y. That means that 10y times 10y would equal 100y squared. And then our last one, we have three pieces here. We have an 81, a p to the 24th, and then a q to the 6th. So what I'm going to do here, sorry this is a little lopsided, is go ahead and put this 2 back in here. So remember, when we have a radical sign without the number, it's implied that it's a square root symbol, or that the root is the root of 2 or the second root. okay, the square root. So we're going to go ahead and take the square root of each of these pieces. So what is the square root of 81? Well, 9 times 9 equals 81. So the square root of 81 is 9. Now, these are numbers that are not 2. So how do we find the square root of p to the 24th or p to the 6th? A nice easy way, so if we think back to chapter 6 in our properties of exponents, remember how if there's an exponent on the inside and an exponent on the outside, we multiplied? Well, remember, this is like an exponent. Okay, so in the reverse problem, this would have been the exponent. So what you're going to do is take this and divide it by the 2. So 24 divided by 2 would be p to the 12. And then 6 divided by 2 would be q to the 3rd. So if you need to write that root in there, that number 2, that is going to help you to remember what you're actually going to be doing. You're going to take the exponent that's inside and be dividing it by the root. And that's the same thing that we're doing here. If the 2 is in here, 2 divided by 2 just equals 1. So that's another thing that you can do. And then when we have roots that are 3 or 4, you're going to be doing the same thing as well in order to simplify these terms. So basically what this is saying is that p to the 12th times p to the 12th will equal p to the 24. And that's true because if you have variables that are the same, you add the exponents. So p to the 12th times p to the 12th, 12 plus 12 equals that 24. In our next video, we'll do a few more examples.